welcome back. Today's goal of this lecture. Today I will see Cauchy Goursat Theorem, which is well-known theorem in complex analysis. Sometimes this is known as actually the Cauchy's integral theorem. To define this theorem, at first I will see what is the simply connected domain. In domain D, consider this curve gamma 0 and we can replace this curve gamma 0 in gamma 1 by deformation. Just increase the radius of the circle, then it would be deformed gamma 0 to gamma 1. We all of us know this is the deformation of curve. Here a loop, that means closed contour gamma 0 can be continuously deformed into the closed contour gamma 1 in the domain D so that it coincides in gamma 1. That means gamma 0 coincides with gamma 1 by increasing radius of the contour. Similarly, in domain D, if we consider gamma 0 is the circle and gamma 1 be the triangle, then we can deform gamma 0 to gamma 1 by just deform it such type. Then we can deform gamma 0 to gamma 1 easily. Notice the picture. Here gamma 0 not be deformed in gamma 1 because here notice there exists an hole. So we cannot deform gamma 0 to gamma 1 smoothly. Deformation of contour is actually a loop gamma 0 continuously deformable to a loop gamma 1 in the domain D if there exists a function zst continuous for 0 less than equal to s less than equal to 1 and 0 less than equal to t less than equal to 1 that satisfy for each s in 0 1 zst parametrizes a loop gamma s in D. Then z0t parameterize the loop gamma 0 and z1t is the parameterize the loop gamma 1. This is the loop gamma 1. As for example, show that the loop gamma 0 where gamma 0 equal to e to the power 2 pi it where t lies between 0 to 1 can be continuously deformed to the loop gamma 1 where gamma 1 equal to 2 e to the power 2 pi it where t lies between 0 to 1 in the domain consisting of the whole plane. For this, consider the parametrization zst equal to 1 plus s e to the power 2 pi it where s lies between 0 to 1 and t lies between 0 to 1. Then z0t equal to 1 times e to the power 2 pi it which is equal to gamma 0 and z1t equal to 1 plus 1 e to the power 2 pi it which is equal to 2 e to the power 2 pi it and this is actually the gamma 1. Here notice the circle deformed into new circle. Here the circle of radius 1, here the circle of radius 2 by this parametrization. I hope my all viewers have clearly understood. This is the actual idea of simply connected domain. If we can do deform any loop easily, then we can tell this is the simply connected domain. Okay, now let's see the definition of simply connected domain. Any domain D possessing the property that every loop in D can be continuously deformed in the D to a point, then this is called the simply connected domain. That means every simply connected domain encloses only point of D where D has no holes. Notice the picture. This is the doubly connected. This picture is the triply connected. And simply connected mean this is the continuously deformed in D to a point. This is called simply connected domain. And today's goal of this lecture, since Cauchy Goursat Theorem, which is known as Cauchy's integral theorem, this is always defined in the simply connected domain. So, indicate what is the simply connected domain. I hope all of you have understood this is clearly. Let's come back our original goal of this lecture, Cauchy Goursat Theorem, which is known as Cauchy's integral theorem. What is the Cauchy Goursat Theorem or Cauchy integral theorem? Suppose a function f is analytic in a simply connected domain D. Then for every simple closed contour C in D, integration fz dz equal to 0. That means if f is analytic within and on C, obviously this C is simple and closed, then in this closed curve, in this closed contour, always if f is analytic, then integration fz dz always equal to 0. As for example, on the curve, on the circle mod z equal to 1, e to the power z obviously always on analytic. So, integration on mod z equal to 1, e to the power z always equal to 0. On the curve mod z equal to 1, sec z always 0 because sec z means 1 over cos z and cos z equal to 0 at the point pi over 2 plus minus pi over 2 plus minus 3 pi over 2. On the curve mod z equal to 1, sec z always be analytic. So, in this curve, integral always equal to 0. This is the Cauchy Goursat theorem or Cauchy integral theorem. I will see the proof of Cauchy Goursat theorem. And by Green's theorem, I will prove it. Cauchy Goursat theorem is f equal to u plus iv, then where u equal to uxy and v equal to vxy. Then integration fz dz means integration u dx minus v dy plus I times integration v dx plus u dy. Now here apply the Green's theorem. Let pxy and qxy be two continuously differentiable function inside the region gamma whose boundary gamma is closed curve. Then integration pxy dx plus integration qx plus qxy dx equal to, by Green's theorem, this is equal to double integration del q del x plus del p del y dx dy. Therefore, apply Green's theorem here. Integration u dx minus v dy plus v dx plus u dy means, by Green's theorem, this is equal to double integration minus del v del x minus del u del y dx dy plus I times double integration del u del x minus del v del y dx dy. By Green's theorem, we can write this. And since f is analytic, then real and imaginary parts always satisfy the shear equation. So, del u del x equal to del v del y and del u del y equal to minus del v del x. Now, notice the equation. Here del u del y replace minus del v del x means plus del v del x. And here del v del y replace del u del x. So, this part 0, this part 0. So obviously that means this whole value is equal to 0. Therefore, the value of integration fz dz on the closed contour C always 0, and this is 0 when the function is analytic. I hope my all viewers have understood the proof. Okay? Oh well. As for example, consider fz equal to 1 over z. Now integrate 1 over z dz. Notice for this, here integration on this closed curve, and here obviously in this closed curve 1 over z is analytic. Obviously this value would be 0. How? Notice, consider z equal to r e to the power I theta. This is r and this is theta. And when the point be vary in this closed curve, then r and theta both would be changed. So dz equal to dr plus ir d theta times e to the power I theta. Okay. Now integrate it. 1 over z means r e to the power I theta, and dz means dr plus ir d theta e to the power I theta. Just cancel this part. Then this value would be integration 1 over r dr plus I times integration d theta. And now since this is the closed curve, so the range would be Ri equal to Rf and theta I equal to theta f. Therefore the range vary Ri to Rf and theta I to theta f. Therefore by integrating, this value is log r, which vary from Rf to Ri, and this is I theta, which vary from theta I to theta f. And since I have considered Ri equal to Rf, and this is true because this is the closed curve, and theta I equal to theta f, 0 plus 0 equal to 0. I hope my all viewers have understood this is. If we consider this closed curve, notice here 0. So 1 over z is not defined at the point 0. So here it has a singularity. At the point 0 it is not analytic. So by Cauchy Goursat theorem, we cannot tell the value would be 0 in this closed curve. But this integral has one value, and this value would be such type 1 over z dz integrate in the circle mod z equal to 1. Similar to before, consider z equal to r e to the power I theta. Then dz would be dr plus ir d theta e to the power I theta. Now put the value 1 over r e to the power I theta dr plus ir d theta e to the power I theta. Then this value would be, just cancel this part. Similar to before, this is equal to dr over r plus I d theta. And since this is the closed curve, so similar to before, Ri equal to Rf, but theta, notice from 0, here this circle means theta varies from 0 to 2 pi. So this value would be 2 pi I. I hope my all viewers have understood. Since this curve is not analytic, whole closed curve, So the value of integral is 2 pi I. Next, consider fz equal to 1 over z square. 1 over z square in this interval, in this closed curve mod z equal to 1, notice obviously fz is not defined at z equal to 0. Since here the integral in this closed curve mod z equal to 1, that means here the radius is 1. So consider z equal to e to the power I theta. So this value would be 1 over e to the power 2I theta dz means I e to the power I theta d theta. That means this value would be I times integration e to the power I theta d theta. Obviously in this here 0 point, in this closed curve theta varies from 0 to 2 pi. So this value would be I e to the power minus I theta d theta integration 0 to 2 pi. This value equal to I e to the power minus I theta over minus I from 0 to 2 pi. Just cancel I. So this value would be e to the power minus 2 pi I, means obviously this value would be 0. Notice here interesting thing, the function is not defined at z equal to 0. That means in this closed curve the function is not be analytic, but the value of integration in this closed curve is equal to 0. Now the question, does it contradict the Cauchy theorem, Cauchy integral theorem or Cauchy Goursat theorem? No. If the function be analytic, then the value of the integral along the closed curve always would be 0. But this is the sufficient condition, not necessary condition. By this example, I have seen this. The function has not defined in the point z equal to 0. So that means the function is not analytic in the whole closed curve. But the value of the integral is 0. So if the function is analytic, then the value of the integral always be 0. But this is not be necessary condition. By this example, we can see this. Okay? Now I will see if z equal to 1 over z in the region half greater than mod z less than t 3 over 2. Here the region is greater than half less than 3 over 2. In this region, notice in this region C is close lying inside this region. For this, consider z equal to r e to the power I theta. Then dz equal to dr plus ir d theta e to the power I theta. Now put the value of dz here, dr plus ir d theta e to the power I theta over r e to the power I theta. This is equal to 1 over r e to the power I theta, similar to before. The equation would be such type, and here theta lies from 0 to 2 pi. And since this is the closed curve, so here the Ri equal to Rf, if then this value would be 0 and this value would be 2 pi I. Notice inside this closed curve, the function fz equal to 1 over z is analytic. But here this is the break, the Cauchy's theorem or Cauchy Goursat theorem, because notice here the contour is not simple connected. So this is break the theorem. I hope my all viewers have understood. Because the condition of simple connected domain is quite essential to apply the Cauchy integral formula. Here, since the domain is not simple connected, so this is break the Cauchy integral formula. Now, I will see another function fz equal to 1 over z minus a. Notice inside A, here the circle, notice here the circle inside A, I want to find integration on this circle. Obviously, in this circle it has some value. Consider z minus a equal to epsilon e to the power I theta. Then that implies z equal to a plus epsilon e to the power I theta and dz equal to I epsilon e to the power I theta d theta. Then theta will be changed. Some point it would be, when theta will be changed, then some point it would be a plus epsilon. Some point it would be a minus epsilon. Hence, different value of theta, the value would be changed. Now put the value 1 over z minus a dz, and z minus a means epsilon e to the power I theta and dz means I epsilon e to the power I theta, just omit this part. Then this value it is, here the integration theta varies from 0 to 2 pi I theta, so the value would be 2 pi I. Similarly, if we consider fz equal to 1 over z minus a to the power n, then dz over 1 over z minus a to the power n, consider z minus a equal to epsilon e to the power I theta. Then that implies z equal to a plus epsilon e to the power I theta. That means dz equal to I epsilon e to the power I theta d theta. Now put the value. Here dz means I epsilon e to the power I theta d theta and z minus a, just put the value, this is epsilon to the power n e to the power I n theta. And this value would be I epsilon to the power 1 minus n integration 0 to 2 pi e to the power I times 1 minus n d theta. Sorry, here theta e to the power I times 1 minus n theta. And this value would be I epsilon to the power 1 minus a e to the power I times 1 minus a n theta over 1 minus n divided by I. Just cancel I. Then this value would be epsilon to the power 1 minus n over 1 minus n e to the power, the value would be 0 to 2 pi I 1 minus n 2 pi minus 1, and this value is 1, so 1 minus 1, this value is 0. Note it to 1 over z square. Here inside A the function is not analytic, but value of the integration is 0. That means, I hope my all viewers have understood Cauchy Goursat theorem. In Cauchy Goursat theorem, simplicity of the function fz in D is the sufficient condition for integration fz dz equal to 0. It is not necessary. If the function is analytic in a simply connected domain, then that implies this integration obviously 0. But When this integration is 0, that does not always imply the function is analytic. That means analyticity is the sufficient condition, not necessary condition. Now I will say if fz is analytic, then the value of integration always depends only the initial and final value of the curve. Notice here the point A and here the point B. If we go A to B by path 1, then integration fz dz, consider this is the path 1 over path 1, this is always equal to the integration of fz dz along path 2. This is equal to integration fz dz along path 2. And we can write this as integration path 1 fz dz minus path 2 fz dz equal to 0. And here notice the minus sign. If we change the direction of path 2, this is the path 2. Here the direction is in the this direction. If we change the direction in opposite direction, then this would be integration path 1 fz dz plus integration over path 2 fz dz equal to 0. That means here part 1 plus part 2 fz dz equal to 0. That means here path 1 fz dz plus part 2 fz dz equal to 0. That imply integration fz dz equal to 0. And this is actually the Cauchy Goursat theorem. Okay. Well, that means Cauchy Goursat theorem is actually path independent. Today I will stop here. In my next video I will discuss some another concept of complex integration briefly. But at first I will highly recommend you please see today's video with pay attention, because this topic actually very important for any competitive exam, also for higher study. Okay, see you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.